Hi, welcome to video 3.2. There'll only be one video from 3.2. It's just two theorems and they're related to each other, Rolle's theorem and the mean value theorem. Okay, so Rolle's theorem and the mean value theorem. And here is Rolle's theorem. Let f be a continuous function, and now you're going to need to justify that by letting me know what kind of function it is: polynomial, radical, rational, trig, and telling me if it's polynomial is continuous everywhere. For these three kinds, continuous on their domain, tell me what the domain is. So the function has to be continuous on the given closed interval, which they will give you a closed interval. The function also has to be differentiable on the corresponding open interval. Now, to be differentiable, all you have to do is show that the derivative of the function is continuous on the interval. If f prime is continuous on the interval, that means f prime exists everywhere on the interval, which means f is differentiable everywhere on the interval. Third condition, f of a has to equal f of b. If all three of these conditions are met, and you have to show me that all three are met, if they're all met, then absolutely there has to exist at least one number c in between a and b, such that f prime of c has to be 0. Now, this is very simple. Basically, it's saying what goes up must come down, what goes down must come back up. So here's an example. I have a point f of a equals f of b. So here's a f of a and b f of b, but f of a and f of b are the same height. The function, as you can see, is continuous everywhere. I'm just going to do it visually for right now. And you can see the function's differentiable everywhere. There's no discontinuities, no sharp turns. Well, what happens is somewhere between here and here, the graph has to turn around and come back down. So here's one example of there being one value of c, such that that's true. Here it starts up, comes down, turns around, goes back up. It could do it several times, so between a and b, it could reach a horizontal tangent line there, another horizontal tangent line there, another horizontal tangent line there. So there would be three values of c between a and b that make the first derivative equal to 0. So here's numbers 11 through 24. Determine whether Rolle's theorem can be applied to the function f on the given closed interval from a to b. So remember, that's the three things. Is the function continuous on the closed interval? Is the function differentiable on the open interval? i.e., is the derivative of the function continuous on the open interval? And thirdly, does f of a equal f of b? If Rolle's theorem can be applied, find all the values of c in that open interval from a to b. And of course, they're being very kind and giving you the conclusion of the theorem, which the AP will not and I will not, which is the value c that satisfies Rolle's theorem is the value of c such that f of c equals 0. Now remember, c has to be between a and b. If Rolle's theorem cannot be applied, explain why not. So here's number 12. It's a polynomial function. That is a square there, sorry. And there's the closed interval. So you have to ask yourself, does Rolle's theorem hold? Is the function continuous on the closed interval? Of course it is. It's a polynomial function, continuous everywhere. Is f differentiable on the open interval, i.e., is f prime of x continuous on the open interval? Well, f prime of x is 2x minus 5, which is a polynomial function, therefore continuous everywhere. Third question, does f of a equal f of b? Well, a is 1, b is 4, so actually plug them in and see what you get. Turns out that f of 1 and f of 4 are both 0. So what the Rolle's theorem holds, there exists, that's what the backwards capital E means, a number c, at least one number c between 1 and 4, such that f prime of c equals 0. Well, f prime of x was 2x minus 5, so f prime of c is 2c minus 5. You get c is 5/2, and of course it's going to work. It has to be between 1 and 4 because there has to be at least one value of c that works. So again, just to remind you, the three hypotheses, the conclusion. Now, the mean value theorem is similar to the Rolle's theorem is what we call a corollary of the mean value theorem. Rolle's theorem has this extra third condition. If we take that third condition away and all we have is that f is continuous on the closed interval and differentiable on the open interval. So here we have, this time f of a does not equal f of b. what it's like taking this example right here and tilting it so that these two lines, in effect, when we say f prime of c equals 0, notice that the slope between the two endpoints, since f of b and f of a are equal, the slope between these 2 points is 0. So basically what you're saying is that the slope at this location here is going to equal the slope between the endpoints. So what we're saying here is not that there's a horizontal tangent line somewhere, but somewhere between A and B, there's got to be at least one point on the graph so that the slope at that point, which is f prime of c, equals the slope between the two endpoints, which is f of b minus f of a over b minus a. So that's the conclusion, is that f prime of c equals f of b minus f of a over b minus a. So here's an example, same directions. Determine whether the mean value theorem can be applied to the function on the given closed interval. If it can be applied, find all the values of c in the open interval such that, and of course they're being very nice in giving you the conclusion. So the first example is a polynomial function. And there's its derivative, which we'll need in a minute. Does the mean value theorem hold? Is the function continuous on the closed interval from -1 to 1? Well, of course it is. It's a polynomial function, continuous everywhere. Is the function differentiable on a, b? Well, the derivative of our f of x is another polynomial function, and that derivative is continuous on that open interval because it's polynomial. So the mean value theorem does hold. There exists a number c in the open interval such that f prime of c equals f of b minus f of a over b minus a. Our a is -1, our b is 1, so that becomes f of 1 minus f of -1 over 1 minus -1. F prime of c, here's f prime of x. Replace the x's by c's. Solve the equation. Now remember, our c's have to be between -1 and 1. And 1 is not between -1 and 1, so the only answer we can keep is -1/3. And that's the end of video 3.2.